Okay, so hope everybody's having a good day, had a good weekend. This is the last week of the 6 weeks, so if you have anything outstanding, like if you still have an assignment to turn in, if it's still within the 10-day time period, or if you're wanting to retake, say, the exam from last week, we have until Thursday morning. We'll go ahead and take care of all that. So there's still a couple of days if you want to come on in. What else do we have here? Yes, I was asked by Mrs. Moore, if you didn't already know, if you're a junior this year and you're going to be taking an IB exam, you're going to need to pay the registration fee of $172, okay, by the 15th of November. So you have, a couple of weeks until that happens, a little over 2 weeks, but you can pay it out in installments if need be. All right, so you don't have to pay the entire amount all at once. You just have to pay. I don't know what the minimum amount would be. Just talk to Mrs. Moore about that, or if you want me to, I can shoot her an email and hopefully she'll get back to me, by tomorrow. We'll kind of see what's going on. But if that applies to any junior in here, who hasn't paid the registration fee yet, go ahead and take care of that. We are not in pre-calculus, so you don't have to worry about the unit circle projects. As far as this week, we are going to be moving on with probability, and we'll definitely get to what's known as conditional probability by the end of the week. And I'm thinking it'll probably take us about a week and a half, 2 weeks to completely get through the entire unit, and then we'll move on to the very next one. All right, but this right here, I'm sorry I haven't had a whole lot of these. In pre-calculus, I'm doing what's known as happy minutes. So I'm timing the students on evaluating trig functions when it comes to the unit circle, and those have kind of replaced the focus activities for a little while because, they got to feel really comfortable with those trig functions. So I haven't been thinking about it a whole lot, but I thought, hey, you know what, we haven't had a focus activity in a while in here. And I'm sure you guys kind of are thinking, hey, focus activity, yay. But because it's the last week, we'll just go ahead and make this one focus activity the next set, and I'll go ahead and count it as a daily grade because that's what we have the least of in the grade book. I think we're going to end up with like 12 or 13 grades overall. So if you have any questions, let me know. Let's go ahead and get to it because I know you want to talk about probability. Okay, so it says suppose our universe is 1, 2, 3, 4, 5, 6, 7, 8. Illustrate on a Venn diagram these sets. Okay, so we have A is only made up of 1, 3, 6, and 8. B is 2, 3, 4, 5, and 8. All right, so we can go ahead and use these. I don't think I gave you enough of those to take care of everything, but at least we have the majority. We don't have to sit here and draw the entire thing over and over again. So let's make this one 1A. Okay. So let's see, the universe has 1 through 8. Let's say this is A, this is B. The first thing I would go ahead and do, is there anything as far as an intersection goes? Okay, 3 and 8. What belongs to this group and to this one as well? So I'd go ahead and say 3 and 8. So we also have in A 1 and 6. So I put a 1 and 6 here. What do we have in B that's not in the intersection? 2, 4, 5. And are we missing anything? Okay, 7. So again, I would just need to place 7 somewhere in the universe in the rectangle, but not in one of those sets. So now we have every member of the universe. Okay. Any questions on that one? Okay. I thought, it's been a while since we're about to get into probability, and it's still going to tie back to Venn diagrams. Probably not a bad idea to run through these and the shadings as well. So let's try B. Okay. So A is now 1, 3, 6, 7, 8. So I'm going to go ahead and make A. Here's B. And B is 3, 6, 8. Okay, so what's in the intersection? 3, 6, 8. Okay, so 3, 6, 8. What's in A that's not in the intersection? 1 and 7. And what are we missing here? Okay, 2, 4, 5. 2, 4, and 5. Now this Venn diagram is perfectly fine, but do you notice some kind of relationship between A and B? B is a subset of A. That is absolutely right. So it would probably be more accurate to go ahead and have one circle inside of another. This one would be B, and I'd go ahead and put 3, 6, 8. And then to finish off A, I'd put the 1 and 7, and then 2, 4, and 5. Okay, but you can still tell from the original diagram that hopefully, B would be a subset of A. Is everybody okay with that? Okay, remember we're talking about a group within a group. Good, good, good. And then now for number 2, we have a bunch of shadings we want to take a look at. All right, so I'm going to go ahead and erase these. I'm just going to go ahead and use these. So you probably have to draw a few down at the bottom, and that's okay. You don't have to draw a lot. So 2A. Let's see. I want to shade the intersection of A and B. All right. And do you guys want to come on up for this? We can? Okay. Do we want to get some folks up here? Do you want to do a train or a random number generator? A random number generator. I like that random number generator. It's completely unbiased. Karime, would you open that door for me, please? While I type in this random number generator. Thank you. Let's see. Yes. Okay. It says end of class. So as soon as we finish up. Oh, man. Okay. What's the highest we go in here? 24? Camille, isn't that your seat number? Okay. So let's see here. Let's go 0 to 24. And I got 18. All right. Okay. Well, this one's pretty easy. We just want to show the intersection of sets A and B. That's all you got to do is shade it. That's it. That's just the overlap. That's perfectly great. That's fine. Okay. That's it. All right. That's A. Now, it looks like in B, I'm looking for an intersection again, but what's that little tick mark? We call it prime. That's the complement. Okay. So we want everything in the universe, but not in set B. The intersection of that with A. All right. Do I have a volunteer or do I click the number generator? Okay. I got 6. Alejandra says, nope, I'll do it. Of course, after her number is chosen. All right, so we want the intersection of A and B's complement. Would be everything outside of circle B. So you're saying it's just that crescent area? What would you guys think? I'd say that's correct, yes. Very good. Okay. Now, remember, one of the things we did when we were looking at this was I went ahead and shaded them separately. Does anybody want me to do that? No? Okay. So, yeah, for B right there, I'd absolutely just shade in this if this was A and this was B. Okay. C. Looks like this time I want the union of A's complement and B. The union of A's complement and B. Do I have a volunteer? Okay. And 13. 12, 13, and Raya's not here today. Okay. 12. All right. This is C. All right. We want the union of A's complement and B. That's a good question. Would we include the middle? Yes. Yes, yes. Because even though it wants the complement of A, we're combining it with everything in B. So the only thing that would not be shaded here would be the crescent, as Alejandro just did. Yes. Okay, good. Good, good, good. Let me move this a little bit further down. And now D. This time I want A union B complement. Okay. Do I have a volunteer or? Okay. All right. Okay, nice. No, that's fine. Looks to me like she's shading everything but the crescent for B. What would you guys say? I agree. That's absolutely right. There we go. Thank you so much. Good, good, good. We're tearing through these. Nice, nice, nice. Okay, so let me go ahead, erase these. Oop, let me get rid of that B. Now we're at E. Okay, so this time I want the intersection of A and B's complement. Okay, so what would that look like? Would anybody like to come on up? Or 15. All right. Okay. Yes. So we want the complement for A and B's intersection. What do you guys think? It looks right to me. It looks like we would shade everything except for the intersection of the two groups. Perfect. Perfect, perfect. Good. And last up we have F. Okay. This time I want the complement of A and B's union. Okay, do I have a volunteer for this last one? Or Gabby, you want to do it? Okay. Let's just see who the lucky person would have been. 18. Caroline again. Oh, okay. Let's see. 6. Alejandra. Okay. 20. All right. There we go. Okay, she just asked, is she doing this wrong? What do you guys think? Looks correct to me. Because the union would be everything in both circles, and we want the complement of that. So everything outside both circles, but still in the universe. That is perfect. Good, good job. Okay, any questions on those? Okay. Now, believe it or not, Venn diagrams are actually going to make a comeback and be very, very useful to us in certain scenarios when we're looking at probability. Okay, so I'll tell you what, I'm only going to take this one for the next set, so make sure your name is on that. Let's pass it up to the front, and that right there will be our final grade for the 6 weeks. Easy, easy.
That'll be the last week.
Mm-hmm. Oh, I'm sorry. Because I'm thinking we could probably go ahead and get the probability assignment in before Friday, but there's no rush. We might as well just put it to the other 6 weeks. Thank you, thank you. Thank you. So you have all those? Okay. Marissa shading? Okay. All right. Thank you. Thank you. Thank you. Perfect. 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 Okay. Oh, and then did anybody look at the grade book? Because I still have this paper here somebody turned in for implication. They graded it, but there was no name on it. Might be Caitlin's. Let's see. That's not yours? Okay. Okay.
No, the handwriting's
Handwriting. Okay.
The handwriting is
way nice.
yeah. Then
That's yours?
No.
Oh. Okay. But if you're looking at, the grade, don't want to show the grade. But if you're looking at the grade book and you are missing that, maybe we just forgot to put our name on it. Okay. Let's go ahead and talk about some probability. Nah, I don't want to say that. Intro to probability. Okay, so today we're going to start out with just some basic probability, which is just the relative frequency of an event. Put simply, it's the number of desired outcomes, what you want, divided by every possible outcome that there is. Now, a lot of people are just going to describe these as odds or chances. I really don't like to go ahead and do that because in some cases it's not necessarily what's happening, but it can be a good description. Like, what are the chances of an event occurring that we want? Okay. And then here's some ideas we want to be aware of. Our sample space, that's every possible outcome of an event. That's considered our universal set. Okay, like for example, if we're going to be drawing a single card from a deck of cards, what would be the universe? How many cards would you have total? Yeah, 52, right? Okay, and then depending on what it is you're wanting to draw. An event, any subset of that sample space. So it has to be within that sample space if you're going to get a probability for it. Mutually exclusive, two events that have no common elements, and we're going to talk about that in just a second. And here are some axioms of probability, just some basic ideas that are going to be really, really helpful to us as we move forward. Okay, so the probability is always going to be between 0 and 1. Okay, so 0 is no chance of that event occurring. So what do you think the one represents? Yeah, 100%, like it's a certainty that's going to occur. All right. The probability of the null set, or the empty set, is going to be 0. Okay, the probability of the universe is going to be 1, because the universe is going to be what makes up your sample space. Okay, so if we're saying the probability of an event occurring within a certain sample space, well, that's always going to be 100%. Now, here are the big ones. Number 3, if A and B are both subsets, remember groups within a group, of the universe and they're mutually exclusive, then the union of the probability of the union, I should say, is equal to the probability of A plus the probability of B. Now, when we're talking about mutually exclusive, okay, what we're talking is there's no intersection. Okay, and I had it written down another way, and it's just kind of going off the top of my head. I forget the definition I put down because I like the way I wrote that. There we go. Cannot occur at the same time. Okay. No intersection. Cannot occur at the same time. Okay. Now, for our purposes today, I'm going to go ahead, once we finish up the lesson, probably tomorrow, I'm going to go ahead and give you another sheet where I'm going to talk specifically about certain events, one of them being mutually exclusive and the other one being called independent, so that you can make sure you understand the difference between the two. But for our purposes now, we're going to say mutually exclusive. That just means there's no intersection, okay, between the two. So number 4, if A and B are both subsets of the universe and are not mutually exclusive, that means we do have an intersection, then the probability of the union is the probability of A plus the probability of B minus the probability of the intersection. And you remember a lot of these rules, they're just repeating themselves back when we were talking about the Venn diagrams. If there is an intersection, you remember we wanted to subtract that off because we didn't want those values to count twice. See, I don't have to do that for the previous one because if there's no intersection, there's no values that are occurring twice. Okay. Number 5, the probability of, what is that? A's complement is equal to 1 minus the probability of A. And that makes sense because the probability of A plus the probability of the complement occurring is always going to be 100%. Okay. So, for example, if I were to go ahead and say I had a coin, if I were to go ahead and flip it, what's the probability of it being heads? Yeah, 50%, 1/2, right? So what's the probability of it not being heads? Yeah, 50%, because that would be the same as the probability of throwing a tails. Okay, does that make sense? Okay, all right.
What does that look like in a bigger set or sample space? Like, can you give an example of where that works?
Actually, we are. I've got one coming up. I believe it's the one in just a second that has the red and white balls. Yes, I've got an example of that coming right up. Okay. So let's take a look at this first example. Or do you just want me to go to that ball example real quick?
Well, even with this one right here where it's red, white, or not white.
Uh-huh.
What's the greater, more variables in the situation?
You mean there's more items?
Yeah.
Oh, it's very possible. But see, no matter what you have, it's always going to be encompassed in your sample space. Just everything possible that could occur.
Yes. What I'm trying to say is saying it's mutually exclusive, and that union of A and B and P or probability of A plus probability of B. Or I'm saying, does that work in a situation where it's not X, Y, and then not X?
Oh, okay. So, like you're talking about the probability of the intersection. Like here with the balls, what would you guys think? Would they be mutually exclusive or not?
They are mutually exclusive because you can have white balls in the red group.
Okay. Well, we've only got 2 groups, so 2 subsets in there. So if I were to graph it, would there be any ball that's both in the red and the white at the same time?
No.
No, so there's no intersection. So what does that mean about mutually exclusive? Okay, mutually exclusive means there's no intersection, right? But sometimes it is possible for two events to occur at the same time. The example with the red and the white balls, this would not be. Because there's no way one ball can be in both the red and the white group at the same time, even though it's part of the largest sample space universe. I don't know if that's answering your question or not.
Sort of, but it's fine.
Okay. Well, let's go ahead and take a look at this one. It says from a bag containing 6 white and 4 red balls, a ball is drawn at random. What's the probability that the ball selected is? Now, especially in the beginning, maybe it's not a bad idea to go ahead and really identify what everything is. What's the number of elements in the universe or items? 10. That means there's 10 balls in the bag, right? Okay, we got 4 red and, 4 red and the 6 white. Okay, and maybe we want to go ahead and list the rest of those. The number of white balls was 6. The number of red was going to be 4. So the first thing it asks, okay, what's the probability if I just blindly look in the bag, am I going to pull out a red ball? Okay, well, the probability is going to be, remember, it's what we want, our desired outcome over everything that's possible. So how many red balls do we have? 4. Okay, out of 10 possible choices. So that would be what? Okay, so we'll say 2/5, so there's about a 40% probability of that happening. Okay, so what this is really saying is, big picture, if you were to go ahead and just do this 5 times, okay, you were to pull a ball out 5 different times. Of those 5 times, 2 of them at least you should have pulled out a red ball if you always start with 10 of this arrangement. Is that making sense? Okay, let's try the second one. This one wants the probability of white. Okay, well, the desired this time is going to be 6 out of the 10. What would that be? Yeah, 3/5. So see, there's a higher probability because there's a larger number of white balls in the bag than red. Okay. Yes, ma'am. You talking about with these right here? Oh, it's very possible that just because of the factors you have, the ratios could simplify where they don't have common denominators, and you don't have to worry about that. Okay. Now, let me go ahead and kind of emphasize one of the axioms that we were looking at just a moment ago. This one right here that's talking about they are mutually exclusive. Okay. The probability of the union happening would be the probability of A plus the probability of B, right? Well, there's no intersection because we just brought up the fact that there's no way one of those balls can be in both the red and the white group at the same time. It's either red or white. So here, the probability of red union white, well, what was the probability of red? 2/5 plus, what's the probability of white? 3/5. Well, 2/5 plus 3/5 would be 5/5, which is 100%. So if you have a bag full of nothing but red and white balls, well, what's the probability that you're going to reach in and pull out a red or a white ball? Okay, 100%, you're going to get one of those balls. Okay, does that make sense? Okay, what would it be if I said the intersection, the probability of the red and white intersection?
0.
That would be absolute 0. There's no chance of that happening. Okay. All right, let's try this third one here. Now, it says not white. So what is this referring to? In fact, what we just reviewed a little while ago.
All the red balls.
There you go. So if I'm talking about not white, I'm talking about white's complement. Yeah. So the probability of getting a not white ball would be the same as the probability of getting a red because it's the only other color in there. Okay. So I'm going to go ahead and say the probability of not white would equal the probability of red, which we just previously determined as 2/5. Okay. And remember, one of the things we talked about a second ago, if I take the probability of an event and I add it to the probability of that event's complement, I'm always going to get what? 1. So it makes sense that the probability of white, which is 3/5, plus the probability of not white, 2/5, remember we just showed that, was 100%. Okay, right, Caitlin?
Yes, sir.
Right. Okay. Okay, let's try another one. Let's go back to this one. Okay, so a fair die is thrown. List the sample space and find the probability of observing 1, a multiple of 3. Okay, well, first off, let's go ahead and list the universe. If I'm throwing a die, what are all the possible outcomes? Yeah, so the universe, I'm sorry?
That's a D6. Is there like 10-sided die?
Oh, no, it just says a fair die. So we're talking about just a normal a cube. Yeah, 6-sided die. Okay. So 1, 2, 3, 4, 5, 6. Yeah, we're not talking about like a dodecahedron or something like that. Nothing like that. That would make a good probability problem, though. Interesting. I don't remember. The name came to me when he said that.
So a dodecahedron, a 20-sided die?
I think so. Pretty sure, right? It's been a long time since I played Dungeons and Dragons, so I don't know.
Well, we just call them D20s now.
D20s?
Yeah.
Really? There you go. Okay. So now I'm wanting to find a probability of rolling a multiple of 3. Okay. So the number multiple of 3. So how many outcomes are there? 2 desired outcomes out of the 6 in the universe. So the probability is going to be the 2 we want out of the 6 total. So there's a 1 in 3 probability of that happening. Okay, so basically a 33.3 repeating chance. Okay. Now, what about an odd number? The number of odd. Okay, that's going to be 3. Yeah. So the probability of that occurring, 3 out of 6, or 1/2. Okay, you have a 50% chance.
Would you like, when we do this on quizzes, would you like us to give you a fraction, a decimal, or a percent?
You know, I'm not going to be a big stickler about that. As long as it's equivalent, like if I've got mine fractional, but the decimal value you have is the same, or even vice versa, I'm going to be okay with it.
Perfect.
Yeah, I'm not going to be a big one about that. Okay, now here's the big question. Are these events mutually exclusive? Now, mutually exclusive, by what we know so far, means it has a intersection. Okay? Oh, does not have an intersection, excuse me. There's no intersection. So if we take a look at multiple of 3, well, we have 3 and 6. Over here, an odd number, we have 1, 3, and 5. So no, these are not mutually exclusive because they have the intersection. Okay. All right. Any questions so far? How we doing? Okay, let's see. We did that one. All right. Now, a family has 3 children. Use a tree diagram to list the sample space, G for a girl, B for a boy, to find the probability that, well, a tree diagram, just like the other diagrams that we're going to become acquainted with, they're just ways of visualizing all the possible outcomes in your sample space. Okay. So can anybody tell me how many outcomes would there be in the sample space for having these 3 children?
There'd be 6 outcomes, right?
No, a little more.
8.
There'd be 8. Okay, there'd be 8 possible outcomes. So,
Oh, I got it.
okay, because let's say, and we're not, we couldn't necessarily talk about, a woman giving birth to triplets. They could all be at the same time, but they're going to come out one at a time, right? So whether they're, the same birth or different births, let's just go ahead. Let's say the first time, you're either going to get a boy or a girl. Okay. You got a 1 in 2 probability of it being a boy or being a girl, but then on the second, you have another 1 in 2 probability after the boy or another 1 in 2 after the girl. Okay, so from here I've got another boy, another girl, another boy, another girl. So this would represent the first birth. This second set would represent the second birth, and then what would I have to do?
For another one.
I would have to draw another set of branches here. Off of each of these four, again, there's the possibility of it being either a boy or a girl. There we go. So if you go along all the branches here, the very first branch, okay, there's one outcome where it could be all boys, right? Okay, what about an outcome where the first two are boys and the third one is a girl? And you'll notice if you go along all the branches, that's where you get the 8 different outcomes. Is everybody okay with that? Okay.
Can't you also like calculate the 8 if there are like 3 opportunities?
And there's only 2 outcomes. Remember, just like we did with the truth tables. Exactly. Yes. That's exactly right. There you go. So do we want to go ahead and list all these individually as I have been, or you just want to go into the probabilities?
Probability.
Just go into the probabilities? Okay. What's the probability that there are going to be 3 boys?
1 out of 8.
Yeah, there's only one outcome, one branch that gives me all 3 boys. So for 1, the probability is just 1/8. I almost tripped on my rug. Okay. Now, do you want to try the other 2 on your own? Just take a few seconds. Let's take 30 seconds. So we're looking for, there are 2 boys and 1 girl. There are at least 2 girls. Now, something to think about on the second one, when it says 2 boys and 1 girl, does the order matter? No, as long as a branch gives you 2 boys and 1 girl, that is a desired outcome. Okay, that's been 30 seconds. So let's go ahead and run through. Let's see how many we should be getting. Well, we want 2 boys and a girl, so that branch works. This branch works. We have the 5th branch works. And I think that's it, right? So it looks to me there are 3 ways to have 2 boys and 1 girl out of the 8 total. Did you guys get 3 8s? Okay. All right, let's take a look at 3. Let me go ahead. It's going to erase my answer I just put on there, but that's okay. There we go. I'll just write that back. All right. Now this one, we want at least 2 girls. So 2 is okay. Is it also okay if I get 3? Yeah, it says at least, so more than that's perfectly fine. So let's see. First branch, no. Second branch, third branch. It's not until the 4th branch that we have our first scenario with the 2 girls. Then the 5th, no. 6th works. 7th does not. Looks to me like the 8th, where we have the 3 girls, works out just fine. So you should be getting. Oh yes, I was just saying if you were paying attention. There you go. So 4 out of 8, which is 1/2.
You can also like kind of check yourself almost, because in 2 it says there are 2 boys and 1 girl, and there are 3 out of 8. So you'd have to assume that it'd be the same if you wanted 2 girls and 1 boy. But you can also adding all girls. So
Oh yeah, that's right. You could absolutely look at it that way. That's a pretty good idea. Okay. Does everybody see what he was saying? Okay. Does anybody want me to elaborate or kind of reinforce that? Okay. Well, good. All right. This is probably going to be our last problem today. Okay. It says use a lattice diagram to determine the probability of getting a sum of 7 on 2 rolls of a die. Okay, so a lattice diagram, that's a diagram used to display the outcomes of a 2-stage event. And a lot of times, a table or what looks to be part of a spreadsheet is going to be really nice to help you out with this. So let me see if I can move this over a little bit. Of course not. I don't know if that's taking place. Maybe I can use the key. There we go. Give myself a little more room there. Okay. So we're talking about rolling what? 2 dice, right? So we could say that the rows represent all the possible outcomes of the first die, and then we could say the columns represent all the outcomes of the second die. So that in the diagram, we could see all the possible sums we have together. Does that make sense? Yes.
Isn't one die but you just rolled twice?
I'm sorry?
Isn't it just one die but you rolled twice? Yes.
Well, 2 rolls of a die, but whether you're rolling 2 die or 1 die and then again, the table is still going to be the same. So yeah, you're right. So I'm going to go ahead and put 1, 2, 3, 4, 5, 6, and then the same across the top. Okay. So what's the number of outcomes in my sample space? There should be 36 different sums I can get. All right. So if I roll a 1 and 1, I have a sum of 2, 3, 4, 5, 6, 7. And then we're just going to go ahead and fill it in. So 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. And then 7, 8, 9, 10, 11, 12 being the largest sum that you can get if you roll 1 die twice or 2 different die. Okay. So this is what's referred to as a lattice diagram. Okay, again, every possible outcome, but here we're talking about the sums. And what are we interested in? Okay, the probability of getting a sum of 7. So for this one, I'm going to go ahead and write it out. The number of elements in my universe are going to be 36. Now, the number of elements that will give me a sum of 7. Okay. How many am I looking at here? Yeah, 6. I can see there are 1, 2, 3, 4, 5, 6 possible ways to make that happen. So the probability of this occurring would be the 6 totals out of the 36 in my set, okay, the universe. So I'm looking at 1 out of 6. Okay. So according to the mathematics here, if I were to take a die and roll it twice, okay, if I were to do that 6 times, at least once out of the 6, I should be getting a sum of 7. Okay, according to this here. That's my probability. Okay, and I think, what is that, about 16 point something percent? Close to 17? Okay. All right. How are we doing?
Good.
Okay, is anybody having a hard time? Okay. What's the probability that you're going to love this lesson? 100%. I love it. There you go. All right. Well, I'll tell you what. I was thinking that one might be our last problem. Do you want to go ahead and try to get another one, or just stop for the day? Stop for the day? Okay, let's go ahead and stop there.
I know it's like late. Like I know it's not like the last 6 o'clock already, but I.
Is it an emergency? All right. If you still have a calculator, let's go ahead and get that back up to the charging station, please.